Welcome to this presentation. In this model, let us have an insight of EMG and PCG. The EMG, that is electromyograph, is an instrument used for recording the electrical activity of the muscles to determine whether the muscle is contracting or not, or for displaying on the CRO and loudspeaker. The action potentials spontaneously present in a muscle are those induced by voluntary contractions as a means of detecting the nature and location of the motor unit lessons, or for recording the electrical activity evoked in a muscle by the stimulation of its nerve. The instrument is useful for making a study of several aspects of neuromuscular functions, neuromuscular conditions, extent of nerve lesion, reflex response, etc. And the electrodes used for EMG are: the EMG is recorded using surface electrodes and needle electrodes. And the surface electrodes pick up the potential produced by contracting muscle fibers. Surface of the skin is first cleaned and then the electrode paste is applied. And the needle electrodes will be inserted into the tissue to study the electrical activity of the muscle. EMG measurements are also important for electric control of the prosthetic devices. This use involves picking up of EMG signal from the muscle at the terminated nerve endings of the remaining limb and using the signals to activate a mechanical arm. This is a most demanding requirement from an EMG since it depends on the working of the prosthetic device. EMG is usually recorded by using surface electrode, as I said earlier. The surface electrodes may be disposable, adhesive types, or the ones which can be used repeatedly. The ground electrode is necessary for providing a common reference for the measurement. These electrodes pick up the potential produced by contracting the muscle fibers. The signal can then be amplified and displayed on the screen of a cathode ray tube. It is also applied to audio amplifier connected to a loudspeaker. A trained EMG interpreter can diagnose various muscular disorders by listening to the sounds produced when the muscle potentials are fed to the loudspeaker. This diagram shows the typical setup for EMG recording. The oscilloscope also displays EMG waveforms. The tape recorder is included in the system to facilitate playback and study the EMG sound waveforms at a later convenient time. The waveform can also be photographed with a CRT screen by using a synchronized camera. The amplitude of the EMG signals depend on the various factors. For example, type and placement of electrodes used and the degree of muscular exertions. The needle electrode in contact with a single muscle fiber will pick up spike type voltages, whereas the surface electrode picks up many overlapping spikes and therefore produces an average voltage effect. A typical EMG signal ranges from 0.1 to 0.5 millivolt. They may contain frequency components extending up to 10 kHz. Such high frequency signals cannot be recorded on the conventional pen recorders and therefore they are usually displayed on the CRT screen. Modern EMG machines are PC based and available in both in console as well as in laptop models. They provide full color waveform display, automatic cursors for marking and making the measurements on the keyboard for access to convenient and important test controls. The system usually incorporates facilities for recording of the EMG and evoked potentials. The stimulators are software controlled. For report generation in the hard copy form, laser printers can be used. The preamplifiers used for EMG are generally of differential type with a good bandwidth. The input impedance of the amplifier must be greater than 2 by 50 megaohms. Present day electronic devices easily provide input impedance of the order of 10 power 12 ohms in parallel with the 5 picofarads. It is preferable to mount the preamplifiers very near the subject using very small electrode system in order to avoid the undesirable effects of stray capacitance between connecting cables and earth. So also any movement of the cable from the output of the electrode will not generate significant noise signals in the cable which feeds into the subsequent amplifier. The preamplifier provides an output with low impedance and therefore high frequencies do not get attenuated even if long cables are used to connect the preamplifier and rest of the machine. The common mode rejection ratio should be greater than 90 dB up to 5 kHz. A calibrating square wave signal of 100 microvolt at a frequency of 100 Hz is usually available. The main amplifier has controls for gain adjustment from 5 millivolt. For selecting the sensitivity most appropriate to the incoming signal from the patient. So, the main applications of EMG are, it is used to study the neuromuscular functions and to know the neuromuscular condition and to study reflex responses and to know about the extent of nerve lessons, and it helps to diagnose the muscular diseases. So the differential amplifier should have a high gain of 10 Hz to 10 kHz. The amplified signal is given to the power amplifier that helps to amplify the signal to a higher level. As I said earlier, the amplified signal may be given to a loudspeaker, tape recorder or a CRO. This diagram shows how the nerve is simulated and the EMG is measured. In the motor nerves, to indicate the location and types of nerve lessons, conduction velocity is measured. So, an electric shock of duration of 0.2 to 0.5 millisecond is stimulated on the nerves. The conduction velocity along the peripheral nerve is measured to calculate the latency. Latency is defined as the difference in time between the stimulating impulse and action potential of the muscle. The conduction velocity is calculated using the formula V is equal to L1 minus L2 divided by T1 minus T2. Normally, the value of the conduction velocity is around 50 millimeter per second. And next, let us have an insight of phonocardiogram.